Okay, so let's continue with our discussion on insulating mold condition for solidification. So we are talking about insulating mold condition. Let me first draw I'm drawing a schematic of the temperature profile that you will see in an insulating mold condition. So there are three layers: mold, solid and liquid. So when we say insulating mold condition, what we mean is that mold insulation properties are the dominating condition for heat flow. So here y is the temperature axis and this is the distance. So when we are talking about temperature, then temperature drop will be only taking place in the mold and not in the solid or in the liquid. So this is Tm and this is T0. So remember the word, we are saying the temperature drop takes place in mold. We are not saying that we have fixed the outside temperature to equal to T0. There is a difference between the two and we will look at that in a moment. So there are some more things that we need to understand over here. What you will see is that the temperature does not drop in the solid. Why is that? Because we are assuming that the solid, remember from the previous class, that solid is very conducting, much more conducting than the insulating mold. Of course it is insulating, so that it has very low conductivity, and since it has very high conductivity, therefore any amount of heat that reaches this point in the solid, which is at the interface, will get transferred directly to the interface of solid and mold. Another thing that we have done here is delta T superheat is equal to 0. See, in actual practice, whenever you are pouring a liquid, you will not pour it at exactly the melting point. It will be a little above the melting point. But for simplification of calculation and to keep the analytical solution simple, we assume that the liquid is exactly at delta T, or you can say just a little above delta Tm, not delta T, Tm, which is the melting point of the material. So it is just a little above the melting point, so it is liquid state. Solid is just a little below the melting point, so it is in solid state, and the temperature drop from Tm to T0 takes place in the mold. I am saying both the things right now, that the temperature drop takes place here, and it is not equivalent to saying that T0 outside of the mold is T0, and at the same time I have also given it as T0, because we have invoked another condition, what is called as semi infinite mold. So for the insulating mold, you remember we talked about three different conditions. One is that or we are inherently assuming some of the we are taking some inherent assumption. One of them is that solid is very conducting, because of which there is no temperature drop here, there is no superheat in the liquid, and therefore the temperature here is also melting point. And insulating mold, so the temperature drop is taking place only in mold, and along with that there is that semi-infinite mold. So what is that semi-infinite mold? Let me draw a little bit to explain that to you. Let us say this is an interface, and it can be any interface, it need not be the solid liquid we are talking about, but just for the sake of comparison with what we are discussing over here, let us say this is the mold and this is the solid. So just at the beginning, what will happen? Just at the beginning, just at the start, mold is at T0, which is the ambient temperature, and solid is at Tm temperature. So the temperature profile is a step function like this. Now as soon as the heat starts to flow, what will happen? The temperature profile will change. It will become like this. So the mold is getting heated up and the temperature near the solid mold interface is rising, and therefore you can see these are the points which have rose. The temperature here has rose from T0 to this point and so on. and this is with increasing time, remember. So we are talking about now at this point there are two things that can happen. So this was the temperature profile, and from this point onward it may happen that temperature, so this is the outside, this is the start of the mold, remember this is distance. I am sorry that I did not label it earlier, but you must remember that this is distance. So this is the outside of the mold, this is the solid mold interface. Now at the outside of the mold, so far we have T naught, but beyond a certain time, again we are increasing time this way, and this is T, this is X. Beyond a certain time the profile may become like this, meaning temperature of the outside of the mold has also increased beyond T naught. Other case, what can it be? So this is again temperature X. Other case could have been that beyond a certain point this will become like this. In this case what will happen is that this is in a steady, you can say it is in a steady state. And why is it different? It is different because here the outside temperature is actually fixed, it is equal to T naught and not actually rising like in this particular case. So these are the two different cases, and physically and mathematically both of them are different. This is actually the condition which we call insulating mold. And this is a particular kind of configuration where you have artificially fixed the boundary condition, that is the mold air interface equal to T naught. So this is you can say I am not giving it any name here, artificially outside temperature is fixed. And this too is actually possible in some kind of casting. What you can do is you can have a cooling mechanism on the outside surface of the mold. For example, you can have a very cold water running around this. So it will have something like 4 degree or 5 degree at the outside of the mold, and there you are artificially fixing the temperature. So this is also possible, but this is not the condition we are talking about. What we are talking about is this condition, which is the insulating mold, where the temperature after certain time it can actually rise beyond T naught. But then why are we interested in this, or what is basically happening over here? If it is not fixed at T naught, how were we able to earlier say that it is T naught? It is because of this condition, semi-infinite mold. So this is insulating mold with semi-infinite condition. Okay, let me write it a little over here. So this is semi-infinite insulating mold. What is different here is that if the time that we are talking about, the time frame that we are talking about is small enough, you can see that the outside of the mold will remain equal to T naught. But if the time goes beyond a certain value, or it becomes very large, then eventually it will start to rise. So when we are talking about the insulating mold, we can say that we are looking only at a condition where the solidification will be so fast or will be soon enough that the temperature of the outside of the mold does not increase beyond a certain point, and therefore we can hold a condition of semi-infinite insulating mold. And this particularly condition means that we are not using any artificial mechanism of cooling the mold from outside. In here, you remember, it cannot be, if you are talking about a simple sand mold casting, which we are doing in our usual laboratory processes, we are not actually using this, because we are not keeping the temperature fixed from outside by any mechanism. It is just the ambient temperature, and if after a certain point the temperature starts to rise, you are not trying to bring it down by any mechanism. So that is why these two are different, and both of them can be used in different conditions. But for now, let us stick with this, which is our insulating mold with semi-infinite mold condition. So that is the semi-infinite mold condition that we are talking about. Now let us get to what we want over here. What we want here is, in the end, we are taking all these simplifications so that in the end we can get an equation of T which is temperature as a function of x and t. X is the distance and t is the time. So we want temperature as a function of distance and time, and since the temperature change is taking place only in the mold, so here we are interested in the temperature inside the mold as a function of x and t. For that, the equation that is invoked is a heat balance equation, and in the heat balance equation that originates from Fourier law gives us the heat equation, which can be written as so the uppercase T is the temperature, the lowercase t is the time, alpha m is also called the thermal diffusivity, and we will see what it composes of. Again, T is the temperature and x is the distance. So this is, if you remember this equation, you must have seen this kind of equation elsewhere in actually diffusion. So this is very similar to the diffusion equation, and that is why this term over there, it is diffusivity term, and therefore in analogy to that, it is called thermal diffusivity in this particular case. So this is originating, this equation is coming from heat balance equation, and from there we get this differential form of the equation, and when we solve this using the initial conditions and boundary conditions, we will be able to get temperature as a function of x and t, and then we can do some more. Once we have temperature as a function of distance and time, we will be able to solve other things. For example, what is the solidification rate, what is the total time taken for a mold, and so on. Okay, so now let us just look at some of the terms over here. So I said alpha m is thermal diffusivity, it is in centimeter square per second. Since this is composed of other terms, and those terms are Km, again you remember, is the thermal conductivity, and the subscript m denotes the mold. So we are talking about thermal diffusivity of mold, and when we say Km, it is the thermal conductivity of mold, rho m means density of mold, and Cm means heat capacity of mold. So for the sake of completeness, I will mention all the parameters that I am talking about here: thermal conductivity of mold and along with the unit, so it is calorie per centimeter per degree C per second. Rho m is density, where subscript m denotes mold. So this will be in gram per centimeter cube. And Cm we have already said, specific heat, of mold, and other parameters we know. T is the time, x is the distance in centimeter. So this is the, you can say, the governing equation that we will use, that needs to be used for getting the temperature as a function of x and t. And remember, this is one dimensional form of that equation. We can also get the 3-dimensional form of the equation or 2-dimensional form of the equation depending on the geometry, but for the sake of simplicity we will just assume that it is a single dimensional object, for example a rod or something like that, and that does not take away any information from us. We can still do all the manipulations to get a form of the equation for this, and you will see, even though this is a single dimensional solution that we will obtain from this, we will be able to generalize it to even 2D and 3D. Next, what we need is to define what are the initial and final condition. So we know the equation, the governing equation, but what are the conditions? There has to be certain, because we are using a simplification, there is most likely certain conditions that we can use over here. So let us look at some of those conditions. Initial condition, meaning what was the temperature profile at the start, we know that part, right. So can we look at those conditions? What is that temperature profile? It is this yellow curve that you look over here, right. This is the temperature profile that was there at the very beginning, and what does it say? If we take this as x equal to 0, and this is the temperature, remember. So if this is x equal to 0, then what it is saying is that at x equal to 0, T is equal to Tm. So we are assuming that x equal to 0 point lies in the solid. So for T equal to 0, that is the initial condition for T equal to 0. So we are talking about for T equal to 0, at x equal to 0, T is equal to Tm. And as you will see that since we are having temperature drop only in the mold, so we are interested only in x equal to 0 to x less than 0 part of the plot. We are not interested in the x greater than 0 part. So at x equal to 0 we have T is equal to Tm. What about the rest? For x less than 0, we can say that T is equal to T naught. So this becomes our initial condition. For any x less than 0, T will remain equal to T naught. That is the starting condition, that is the initial condition. That is one thing that is set up. And remember, these initial and boundary condition are also useful when you are trying to formulate this problem using some finite element method, for example using MATLAB. Although we will get an analytical solution here, but you can also get the numerical solution by using some finite element method using first principle. So you will not have to solve the analytical solution, you can just directly go back to your fundamental equation, which is the governing equation, which we called as equivalent of the diffusivity equation. So you can use this, use the finite element method and get the solution for not only this, even for more complicated conditions or complicated temperature profile. So that in that sense, initial condition and boundary condition are important to be known. Now boundary condition is something that will be true for all times. So for all t greater than 0, what are the things that we can say? One thing that we can say is that it is a semi-infinite, and we said that at very large distance the temperature will always be T naught. We are not saying at this particular distance, this is not a real infinite distance. At a real infinite distance, which is x equal to minus infinity, T will be equal to T naught. That is another boundary condition that we are invoking over here. And another thing that we are invoking over here is again that x equal to 0, T remains equal to Tm. So we have our initial conditions and the boundary conditions. If you use this, then you would see that there are very standard solutions for this kind of equation under those conditions. And what is that solution? So let us look at. So the solution you may see would be of this form, and this is just a general solution that you can obtain for a differential equation of this form. ERF is the error function, so this is the final equation, and you see this what we are getting is t as a function of x and t, which is what our initial goal was. So we are able to get temperature as a function of x and which is distance and time, and this is that equation where ERF is the error function. Since we are talking about error function and some of you may not be aware of the error function, so let me give you some values that you may find interesting. One is that ERF 0 is equal to 0 and that ERF infinity is equal to 1. If actually if you use these two values of ERF, you would be able to cross check that all your initial and boundary conditions are actually coming out to be true. How? Let us see. ERF 0 is equal to 0. So this is our solution. Now how will this term be 0? It can be 0 if we put x equal to 0. And what do we have at x equal to 0? At x equal to 0 we have t equal to tm for all time, for t equal to 0 and for t greater than 0. So at x equal to 0, t should come out equal to tm, and we can get this term whole term as 0 by putting x equal to 0 no matter what the value of t time you put over here. So this will be 0, and which means ERF, the overall value of this function would be equal to 0. Therefore t minus tm will be equal to 0, therefore t will come out equal to tm, right. So we actually do get t equal to tm when you put x equal to 0. Another thing, if you put t equal to 0, which is the small t, the time t, if you put this value equal to 0, this whole thing becomes infinity. And if you have ERF infinity, then you know that ERF infinity is equal to 1. So this value becomes 1. And before I get to the final solution, let us see what do we have for t equal to 0. For t equal to 0, for whatever x you use, you should get t equal to t naught. Okay. So here if you put infinity, this will become, this whole thing becomes 1, and that means t minus tm is equal to t naught minus tm, which means t equal to t naught. Therefore this is again coming out what we expected. At x equal to 0, t is equal to at t equal to 0, for all x less than 0, t is coming out to be t naught. So no matter what value of x you put here, actually in the negative only, if you put whatever negative value of x you put over there, you will get t equal to t naught. So this is also coming out to be exactly as you would have expected. So this equation that ensures that our equation is all right. So now let us move on to the next stage. We have the form of the equation for this insulating mold condition. Why not make use of it to get some more information from this. So what are those information? We will see. One of the things that you can obtain is how much solidification would have taken place in a given time. So how do we get to that? So for that we will have to use our equation this is, you can say, similar to second law of Fick's, although there is nothing like that, but that what is commonly referred to as Fick's second law, this is in the same form. If we call that the Fick's first law, this becomes the Fick's second law, and this is your Q over A equal to minus Km del T over del X. What it is saying is, what is the heat coming or going into an interface that can be obtained as a product of conductivity times thermal gradient at that point. That means that if we use our sand mold and solid condition and assume that there is some temperature profile, what we are trying to do next is trying to equate what is the heat going into this mold, and we will also get to that value of heat by a different method and then equate these two, and when we equate these two we will be able to get the length of solidification as a function of time. Let us move on. So, this is our equation Q over A is equal to minus Km del T over del X. So, what we need is to differentiate our equation, which is this equation in with respect to x. How do we differentiate del T this function with respect to s? So, for that you also need how do we differentiate ERF function. So, again a quick bit of information. So, this is differential, not del. Differential of ERF x is given by now. If you know this, then we will be able to differentiate our this equation. Now, if you look at this equation, if you want to differentiate it this way, you will have to invoke what is called as chain rule. So, this is ERF is a function of something which is a function of x. So, it is a function of x. Temperature here is a function of x. So, if h is equal to f of g of x, then what we are saying is that first differentiate h with respect to g and then differentiate g with respect to x, and then we will be able to obtain the equation or obtain the final differential form of t with respect to x. Let us move on, and we have del t. If you use this, we can you can see that this is how it will come out, del t over del x. First we are differentiating with respect to we are differentiating x with respect to g, which is this form, and then differentiating g with respect to x, actually vice versa. This is differentiating g with respect to x and this is differentiating h with respect to g. And there is a Tm minus T naught term over here. So, see, we have used this equation and this fact that differential of ERF x is given by this, and also we have used the chain rule of differentiation. So, we are able to get del T over del x, and there is this Tm minus T naught, which is actually from here, and there would also be Tm, but when you differentiate with that x, that becomes 0. So, we are only left with these terms. So, this is our del T over del x, which is just one part of it. If we want to get Q over A at x equal to 0, it is equal to conductivity times gradient at x equal to 0. So, next thing we have to do is we have to put x equal to 0 in over here. So, if you put x equal to 0 over here, you can see that as you put at x equal to 0, you get I am putting the equation, and you can easily see that it comes out from the above equation. So, this is the del T over del x at x equal to 0, and then we will have to multiply it. So, we will come back to this in the next lecture. So, we will leave it over here and we will use the same equation in the next class. Okay, thanks.